Okay, so now we're going to talk about oxidation and reduction. And this is a way of classifying reactions by watching what happens to the electrons. So we know that ionic compounds form when one element will give away electrons and another one will take electrons. And we know that covalent compounds occur when elements share electrons. So if covalent compounds get rearranged, then maybe that sharing arrangement has changed. And so we can track what happened in a chemical reaction by tracking what happens to the electrons. And that's the basis of our oxidation and reduction reactions. We call them oxidation and reduction because they always happen together. And these are the two things that happen. Oxidation occurs when something loses electrons, and you know they have to go somewhere, right? And reduction occurs when something gains electrons, and of course they have to come from somewhere. And so in a reaction, if something is losing electrons, something else will be gaining them, so they come together. Sometimes you'll hear these called redox reactions or oxidation reduction, and it's because they come together. Now, you might think that's weird to call it reduction if you're gaining something, but remember that electrons have a negative charge. So if you're gaining a negative charge, your charge goes down, the charge is reduced. Hence, that's why we call it reduction. All right, so we have kind of, I think, a generally good handle on this in very simple ionic type equations. So let me put this up here and we can kind of see what I mean by that, because we actually did something like this as an example to show you how ionic equations occur. So if you have elemental sodium and elemental chlorine, the charge on these elements is 0, right? Because there's not a charge shown, you know that the charge on each of these is 0. If they had a charge, I'd have to show it. But then in the sodium chloride ionic compound, the charge on the sodium is a +1 and the charge on the chlorine is a -1. So we can just use the actual charge of the elements and the charge of the ions in the ionic compound to tell us something about where the electrons came from or where they went to. Can you look at this and tell me which one of these things lost an electron and which of these gained an electron? Sodium lost an electron. How did you know that sodium lost an electron? Well, because it's in group 1 and it likes to lose an electron. But aside from that, yes, Sarah, aside from that, if you're looking at just the equation itself, and you see on this side it's 0, and on this side it's +1, it must have lost a negative charge, right? So this was oxidized. It underwent oxidation reduction. Okay, that was oxidized. This is a little bit bigger than I need it to be. Okay, and then of course, since they come together, you know, something else must have been reduced. Does it make sense to look at chlorine and say that it was reduced? If the charge went from 0 on each chlorine to -1, then it must have been reduced. Now, Sarah has asked a really good question. She says, wait a minute, is this equation balanced? And the answer is no, I haven't balanced this equation. I don't have to in order to track oxidation reduction, but it won't hurt us to do it, right? Might be good practice anyways. If I did balance it, what should I do here? I'm gonna need, since I have 2 chlorines in my Cl2, because this is one of my elemental species that exists as a diatomic species, I'm gonna need 2 NaCl's, which means I'm gonna need 2 NAs. Okay, now it's balanced. So it shows us that 2 sodium atoms interact with 2 chlorine atoms in the 1 chlorine molecule to give me 2 NaCl molecules, quote unquote molecules, because it's an ionic compound, so they don't exist as distinct molecules. So the point of this section then is to say that the sodium was oxidized, and the chlorine was reduced, and hopefully you can see that based on the charge, right? Now, we're not going to rely on the charge. We're going to rely on something called the oxidation number. But the oxidation number for ions in ionic compounds, it's exactly the same as the charge, and you can kind of see it here, so in the charge. So thought we'd start there. It's exactly the same. So here are the rules for assigning oxidation numbers. Nicole, you're exactly right. The sodium lost electrons because it went from a 0 to a positive, so it must have lost negative charges, right? And the chlorine gained those electrons because it went from a 0 to a negative charge, so it must have gained those negative charges. Do you see it? And you can see it in the change in the charge, because when you lose electrons, you become more positive. Yeah, and if you gain electrons, then you will become more negative. There we go. Okay. Oops. There we go. All right, so here are the rules for assigning oxidation numbers. And then once we assign oxidation numbers, we can just compare what they become to see what was oxidized, what was reduced. And what you'll see, most of these will be pretty straightforward. If you're a neutral element, that is like these ones, standard state neutral, you don't have a charge, so your oxidation number is the same as the charge, which is 0. Okay. And if you are an ion, or if you're in an ionic compound, so this is an ionic compound which is composed of individual ions. So the oxidation number of each ion is just the same as the charge of the ion, just like we did here. All right, this is also just like when we were putting together ions to make ionic compounds. We said the sum of your individual charges was your overall charge. Same story, the sum of your individual oxidation numbers, which are basically ionic charges, is the same as the overall charge, right? So the sum of the oxidation numbers must equal the overall charge. Now this is the only point where it gets weird, okay? This is the only point where there's anything different going on. And that is that we also would like to be able to track electron movement in covalent compounds. And so we want to be able to assign oxidation numbers to covalent compounds. But covalent compounds don't have charges like ionic compounds. So we're going to follow these rules to assign an oxidation number. It's going to feel a lot like assigning a charge. Even though we're not technically assigning a charge, it's kind of like assigning a charge. And here's what you have to do for covalent compounds. You're going to go in this order. If there is a hydrogen, it gets to be +1. And then you have to default to the third step here to determine what else was attached to it, was the oxidation number of that. If there's not a hydrogen, then you look for a fluorine, and it gets to be -1. And then anything else that's attached, you have to follow the rules here. If there's not a fluorine, then you look for an oxygen, and so on and so forth. So this is an ordered list by priority, and the hydrogen gets to be +1 first. And if there's not one there, then the fluorine gets to be -1, and so on and so forth down the line. So if I was just looking at individual compounds and not reactions, I can assign some oxidation numbers. It might be helpful just to practice a few of those. So I'm gonna, give me just a minute. I've got a worksheet from a different class I'm gonna pull up here that might actually be a little bit easier. Sorry, just a second here. Okay. I'm gonna pull this over here. I'm gonna pull it down here. Assign oxidation numbers to each atom. So for lithium here, what would the oxidation number on lithium be? This guy right here. Careful, Sarah and Nicole. It's not +1 because this is not a lithium ion. If it was a lithium ion, I'd have to show you a charge. So because I didn't show you a charge, there's not a charge there. We're talking about elemental lithium. Oh yeah, see down here how I showed a charge on this bromine, showed a charge on the calcium. So if it formed an ion, it would be a +1 ion, and the lithium ion would have an oxidation number of +1. But the lithium element, because it's a neutral element in its standard state, it's all by itself, then it has what oxidation number? Yeah, 0. Perfect. All right, what about this F2? What about the fluorine atoms here? They're also 0. Good. What about this bromine ion? What's its? Oh, Nicole's got it. -1. Perfect. And this calcium ion? Just the charge of the ion. Perfect. All right, that's not too bad. All right, let's look at this compound, calcium carbide. This is an ionic compound because it's got a metal and a non-metal. We know that the calcium is what? It's +2 because it's in group 2, so it's always +2. All right. Now, the sum of the oxidation numbers is equal to the overall charge. Since this is a compound, it's neutral. What would the oxidation number on each of those carbon atoms have to be? Perfect, -1. Because -1 times 2 gives me a -2 to balance out the +2. Again, it feels exactly like we're assigning an ionic charge. And the difference is it's not truly an ionic charge, right? Because carbon doesn't make a -1 ion, ever. That doesn't make any sense, right? For where he is on the periodic table. But for the oxidation number, that's totally fine. All right, let's look at NH3. Ooh, this is a covalent compound because nitrogen and hydrogen are both nonmetals. So we're going to have to follow the rules here, right? So following the rules, it says first, if there's a hydrogen, it gets to be +1. So my hydrogen must be +1. Which means, since there's 3 of them, that the nitrogen has to be what? -3. Now that's not too bad, because if they made ions, I would expect that to be -3 and +1. So it's kind of like an ion, but still it's just the oxidation number, because we know that they don't actually exist as charges like that in this compound. All right, C2H6, again, 2 nonmetal, so it's covalent. We're going to follow the rules. There is a hydrogen. So the hydrogen gets to be what? +1, good, Nicole. And that means that each carbon there would have to be, good, -3. So 6 carbons each, 6 hydrogens each at +1. We're going to be balanced by 2 carbons each at -3. Good. Okay, XCF4, that's bizarre. Look, xenon and noble gas making a compound. Cool. All right. Does that really happen? Yeah, it does. It does. Okay. For xenon. You wouldn't see that with neon or argon. All right. So still covalent because those are both nonmetals. Is there a hydrogen? Not a hydrogen. Is there a fluorine? Yeah. So the fluorine gets to be -1. You guys have got it. Which means that the xenon here must have an oxidation number of +4. Okay. All right. Ooh, feeling pretty good. All right, now let's get tricky. Polyatomic ion here. Ooh. Polyatomic ions are held together with covalent bonds. They're nonmetals here. We can even draw Lewis dot structures for them. So we're going to follow the same rules. Is there a hydrogen? No. Is there a fluorine? No, only because there's neither of those, I can say the oxygen gets to be -2. All right, this oxygen gets to be -2, and there are 3 of them for a total charge of -6. And the whole thing overall has a -2 charge here. So the carbon must have perfect +4. Well done, Sarah. That gives you the +4 -6. Leaves you with the remaining -2 charge, because the sum of the oxidation numbers is going to be the overall charge. Did that make sense to you guys? Yeah, it just takes practice. We can do it. Let's do it. Here's another one. Nicole, sulfate polyatomic ion. Again, it doesn't have a hydrogen or a fluorine. So we're going to assign the oxygen, gets to be -2, and use the rest of this to deduce what the sulfur must be. All right, Sarah tells me it's +6. How did you come to that conclusion, Sarah, that the sulfur is +6? Oh yeah, Sarah just did a little equation here. And she says, look, my total charge has got to equal, sorry, the overall sum of the oxidation numbers has to equal the total charge, which is -2. And then she says, I've got 4 oxygens, each at -2. And then I'm gonna add whatever the sulfur is, let's call that X, and I'm just gonna solve for X. And -8 plus what gives me -2? And she says, that's gotta be +6. That's great. You guys can totally write a little algebraic equation here to see how that works. You with us, Nicole? Excellent. Yeah, it never hurts to write this little equation. Okay, these next two take this a step further. Now I've got a polyatomic ion, but then I'm also associated with another element here. So NH4Cl, even though it looks like it all has nonmetals, hopefully you recognize the NH4 is a polyatomic ion with a +1 charge, and chlorine is an ion that's going to make a -1 charge. So this is an ionic compound which contains a polyatomic ion, which is held together with covalent bonds. So we're going to have to do some extra fun. We're going to have some extra fun picking this guy apart. What shall we do? I think first it's wise to recognize that this is an ionic compound with 2 ions, because that will help you immediately assign the chlorine as an ion with an ionic charge of -1. It's got to have the oxidation number of -1. Okay, Nicole's got a good question. She says, with the polyatomic ion, would you just use the charge it gives you, or do you pick it apart because that's covalent? Yes and yes, right? You have to use the charge because the sum of oxidation numbers has to equal the overall charge. And you do have to pick it apart this way because it is bound covalently. So in both of these cases, for the carbonate and the sulfate, I said, look, it's got to equal, my sum has got to equal this overall charge. That's an important part of it. And then because it's covalent, I had to start with the oxygen to say the oxygen got to be -2. So if we did it here, the oxygen got to be -2, and there were 3 of them, right? So that gave me a total of a -6. Well, that looks terrible. Tell you what, there we go. There were 3 oxygens, each at -2. And then I'm trying to solve for the carbon, because that's the thing that I don't know. But the total sum of that has got to equal -2, because that's the overall charge. And that's where I say, okay, well, that's going to be -6 plus x is -2, so x would have to be a +4. So I'm doing both of these, picking it apart, and I'm looking at the overall charge as being 2 because it's a polyatomic ion. Does that kind of make sense? Okay. Now for this one, we can do the same thing. We already assigned the chlorine. We can pull this out here and, oh geez, I should just use the text tool all the time. NH4 plus, okay. So the NH4 plus is associated with the chloride. We know what the chloride is, but since there's 3 elements, we kind of have to take it piecemeal. So I pick off the chloride, I assign that, and now I can assign the NH4 plus, and I see that because it's a polyatomic, I'm gonna follow the rules for covalently bonded things. which means perfect. Yes, the H gets to be +1. Exactly right. So H gets to be +1, which means that the N gets to be oh, this is tricky. Hang on a second. There's 4 hydrogens, each at +1. So that gives me a total of +4, right? 4 times +1 plus, I'm solving for the nitrogen, and the total sum has got to be 1. So that becomes 4 plus x is equal to 1. So x, my nitrogen, is -3. The nitrogen has to be -3 to cancel out 3 of the 4 positive charges to leave me with 1 positive charge overall at the end of the day. -3 on the nitrogen, +1 on the hydrogen. Now, of course, if we did this right, this neutral compound should have a sum of oxidation numbers that is equal to 0, which it does, right? -3 plus 4 minus 1 is equal to 0. We got it. Does that make sense? All right, ish. Let's do it. Let's do this one. Sodium sulfite. How would we assign these guys? Oh, this is a inside of a compound, so sodium is going to be an ion, because if you've got a metal bound to anything, then it's going to do so ionically. So the sodium ion, yeah, is always going to be +1. Good. Excellent. And then what? We're going to pick apart the SO3. Okay, good. What do we know? What do we get to assign? The oxygen's -2 because there's not a hydrogen or a fluorine. Good. And there's 3 of them at -2. That gives that a -6. So what does the sulfur need to be? Close. Close, Sarah. Sulfur's not +5 because there's 2 sodiums here, not just 1. Yeah, +4. So you can either do the entire thing together, that is counting, you know, the +2 from the sodium, -6 from the oxygen, that tells you what sulfur is. Or we could have pulled it apart over here and said, okay, SO3, we're looking at the sulfite polyatomic ion, so it's got a -2 charge. And then we say -2 times 3 is -6. And that's got to be a +4 in order to leave us with a -2 charge. Either one of those would work. Okay, so now that we've done individual atoms inside of molecules, just to assign oxidation numbers, like this is the hard part. The rest of it is relatively easy. If we can assign individual ones, then I just look at what changes and tell what gets oxidized, what gets reduced. So let's do this with the formation of calcium chloride here. So calcium here, what would the oxidation number be? He'd be 0 because he's all by himself and he doesn't have a charge, right? If he had a charge, then that would be the charge. But if there's no charge, then it's 0. Perfect. What about this chlorine? Also 0. Excellent. All right. Calcium chloride. What do you see? 2+ on the calcium because it's an ionic compound and calcium's in group 2. Good. And -1 on the chlorine because it's in group 7. Excellent. Okay, so what changed? Which elements have different oxidation numbers? The Ca went from 0 to +2, so it became more positive, so it was oxidized. Good. And the Cl went from 0 to -1, it became more negative, so it was reduced. Once you got the numbers, the rest of it just tells the story. It's very easy to see. Okay, let's do this next one. Potassium hydroxide goes to form potassium oxide plus water. So we're going to assign oxidation numbers to each of these guys. So let's do the KOH. Yep, ionic compound. Potassium's a group 1 metal, so it's got to be +1. Here's my hydroxide polyatomic ion. Good, so that hydrogen gets to be +1 because it's listed first. And then I just deduce it based on the fact that the overall thing has to be the overall thing, right? So that means that the oxygen is left with a -2 here. Excellent. Okay, so let's look at the product here. K2O, potassium oxide. Let's assign oxidation numbers here. +1 for the K, good. Still an ionic compound. -2 for the O, it's an ion all by itself in an ionic compound. Okay, what about the water here? Covalent compound. Good, hydrogen gets to be +1, and the oxygen then gets to be -2. Perfect, all right, so what changed? Nothing. This is a trick question. Nothing changed. The potassium is +1 on either side. The oxygen is -2 on each side. Hydrogens are all +1. So this is not an oxidation reduction reaction. And you can tell that it's not because the oxidation numbers are the same. Okay. The numbers don't lie. They are what they are. Excellent. Okay. Let's try this guy. Sulfur dioxide reacts with elemental oxygen to form sulfur trioxide. So here, what are we going to do with this SO2? Oxygen gets to be -2, perfect. Which means the sulfur must be +4. Good. 2 oxygens, each at -2. It's got to be balanced out by a +4. Okay, what about this oxygen right here? Oh, good, that's 0. Excellent. Okay. And what about this SO3 over here? -2 for the oxygen again. Good. Excellent. Which means that the sulfur there has got to be not a +4. Hang on a second, just to check. I'm making the neutral molecule sulfur trioxide. I'm not making the sulfite polyatomic ion. Yes. So the oxygen gets to be -2, not the whole molecule, yes. Which means that the sulfur gets to be +6, so that the overall thing is 0. Okay, good. All right, so what changed then? What was oxidized? What was reduced? Yeah, it's a super easy mistake to make. It's okay. That's how I knew what was going on in your head, right? That's how I knew to say what I did, is because it's easy to look at SO3 and assume it's a sulfite, because you memorized those, and good. I want you to memorize them. Just always make sure that you're looking for the charge up here, right? If there's a charge, it has to be shown. Yeah, so the sulfur went from +4 to +6. So clearly the charge became more positive, and that means that it was oxidized. Excellent. And if it gets oxidized, something else has to be reduced. And this is a little bit tricky. You're exactly right. Oxygen was reduced, but not every oxygen was reduced, right? Because these oxygens are -2 and these oxygens are -2. So some of the oxygens stayed the same. But this oxygen, the oxygens that came from the elemental oxygen, those ones were reduced. Perfect. Now this is not a balanced equation, right? If we balanced it, we would come along here and we would say, I'm going to need 2 of these and 2 of these. And that would give me 4, 6 oxygens. Okay, so of the 6 oxygens that were in the reactant side, only 2 of them were reduced in order to reduce both of those sulfurs. Okay, how are we feeling about these? Oh, good, good. I'm glad that you said that, Nicole. This is one thing to help you remember. Oxidation is losing electrons and reduction is gaining electrons. I like it because it's short and sweet, oil rig. The only thing I don't like about it is that it doesn't say electrons. So when you say losing what, gaining what, like you have to realize what that means. I once heard there's another one, like Leo the lion says grrr, which is losing electrons, oxidation, that's Leo. Gaining electrons, reduction, that's the grrr. And I think that's too complicated to be helpful, but I still remember it, so maybe it is helpful. That's just another losing electrons. Oxidation says gaining electrons, reduction. This at least maintains that electrons thing in there. But however you memorize it, pick one that works for you and stick to it. Okay, well, we've got those are just from the lecture notes. We've got a bunch more from your worksheet. Do you want to go over some more of these? How do you feel? What do you think? Just the tricky ones with the covalent compounds. That could be helpful. Or you're like, nah, I got this. Okay, yeah, let's do more. We've got a few minutes more. Let's do, I'm gonna go over here just because I know which ones are tricky. These last 3 are really tricky. And then let's do this one as well. Maybe this one. Okay. All right. But let's make sure that we get these ones first. So if we're looking at, we don't need to do this one. Let's just start with this one. This is hydrogen peroxide. It spontaneously decomposes to form water and oxygen. That's why they sell hydrogen peroxide in brown bottles, by the way. is because light helps catalyze that decomposition. Okay, so here we go. Hydrogen peroxide decomposes to form water and oxygen, and we want to follow the electrons here. See who owns what gets oxidized, what gets reduced. So let's start on this side, and we're following the rules, right? H2O2 is a covalent compound, and this says for covalent compounds, use the following assignments in exemplary disorder, blah, 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 blah. Hydrogen gets to be +1, fluorine gets to be -1, and so on and so forth. So what am I going to do here? Hydrogen's +1, because this is a covalent compound and I have to go in order. Excellent. What does that tell me about the oxygen? Yes, that's exactly right, Nicole. It has to be -1. Once you assign the hydrogen, then you go back up a step and say the sum has to equal the overall charge. The overall charge is 0. This is a neutral compound. So because I have 2 hydrogens at +1 and 2 oxygens, each of them must be -1. Now that's going to feel weird, right? Does it feel weird? I think it feels weird because you didn't say it is -1. You said, from that, it makes me think it's -1. It is weird because you're like, no, oxygen always gets to be -2. Well, that's true if it's an ionic compound, yes. But if it's a covalent compound, then that's not necessarily the case. And that's why we follow these rules very carefully, okay? So in this one, the oxidation number, not the charge, but the oxidation number is -1. Perfect. All right, so then we go to form our products and we see for water, what do we do? Hydrogen is +1 again. And now it feels like the universe has righted itself because 2 + 1 means that one oxygen gets to be -2. Phew. All right, what about this oxygen then? It's 0 because it's elemental. It's all by itself. Perfect. All right. The fact that this has an oxidation of -1 is part of the reason that this is not a very stable molecule and it decomposes spontaneously. What changed? Well, if something was reduced, then something else has to be oxidized. And if something was oxidized, something else has to be reduced. So the hydrogen did not change. You are correct. The hydrogen was not reduced or oxidized. Once we put down the numbers, that was the hard part. Now we're just going to look at the numbers, and the numbers tell us what they tell us. And they say hydrogen was not oxidized or reduced. I'm going to balance this reaction while you're looking at it. Okay, so the O2 from the H2O2 is oxidized to make elemental oxygen. The charge became more positive, right? I must have lost an electron to go from -1 to 0. Perfect. Oxidized. Excellent. Well, if something was oxidized, something else must have been reduced. Because if I got rid of some electrons, they have to go somewhere. Perfect, Nicole. The O2 from the hydrogen peroxide was also reduced to make the oxygen in the water, because here, if we're just looking at the numbers, here I'm going from a -1 to -2. I'm becoming more negative. I must have gained electrons. That's reduction. So if I'm looking at the numbers, oxygen's -1 here, it's -2 here. That changed. It was reduced. Or I could say oxygen is -1 here, it's 0 here, it changed, it was oxidized. So I just love this problem. It's amazing. It's so fun to see oxygen be something other than -2 and then see oxygen both reduced and oxidized. Now, wait a minute. Was it the same oxygen that was both reduced and oxidized? Like the same oxygen atom here was reduced and oxidized? No, yeah, because there's 2 molecules and each one has 2. So of the 4 oxygen atoms, 2 of them were reduced to form water and 2 of them were oxidized to form oxygen. And we just, after we assign those oxidation numbers, we just follow the numbers and say that's what happened. Perfect. That one was really tricky. And you nailed it, Nicole. Great job. That is it. Does anybody else have a question on that one? It's a thing of beauty. Well done. All right, if you guys feel good about that, then let's try this one. This looks like fun. We'll start with the sodium. Give me oxidation numbers. Perfect. +1. Excellent. I'm going to make this red. What else do we know? Good. Oxygen's in that covalent compound. There's no fluorine or hydrogen, so it gets to be -2. Okay. There's 3 of them. So the nitrogen Oh, close. Close. Now, if the nitrogen were to fully cancel out the oxygens, it would be +6, but it doesn't because this is a polyatomic ion with a charge of -1, right? And or you could say when it's paired together, you have this +1 as well. The whole thing overall has to be neutral. Perfect, you got it, +5. So +1 from the sodium, +5 from the nitrogen, -6 from the 3 oxygens, each at -2. That gives me my neutral sodium nitrate compound. Okay, let's do it again on this side. Sodium's +1, perfect. Oxygen is -2, excellent. Which means that the nitrogen on this compound is +3. Oh, you got it. Right on. Well done. Okay. What's this oxygen? 0. Perfect. All right, that was the hard part. Now we just look what changed. Good, the nitrogen went from +5 to +3, so it must have been reduced. Okay, something was reduced, something else must have been oxidized. Yes, so that is the oxidation product, and it came from here. Now there is more than one oxygen on the stage, and we did not balance it. We could. We don't have to, we really don't. But if we did balance it, we would have, I think, two of these, that gives me 6 oxygens, that's 4 plus 2. Okay, so of my 6 original oxygens, 2 of them will be oxidized, and the remaining 4 will just stay as is, and they're not oxidized or reduced. Great work, Nicole. How do you guys feel about these? Good, awesome. All right, so we will pick this back up on Tuesday. And on Tuesday, we're going to introduce, let's see, on Tuesday, we're going to introduce precipitation reactions and acid-base reactions. So we're going to do the rest of this worksheet, but also I skipped this section right here, the section 2, classify. When we have done introducing precipitation and acid-base, once you've seen all of precipitation, acid-base, and then oxidation reduction, we can go look at this and classify these as well. So for practice, do section 3 of your worksheet here, assigning oxidation numbers, and all the rest of section 1 of your worksheet for balancing will be good for you. And have a great weekend, guys.